So in video 3, we're going to define the trigonometric functions in terms of the xy plane. We've already done it in terms of a right triangle. We're extending the definition into the xy plane. Before we do that, we want to identify that given any xy coordinate in the xy plane, and it wouldn't matter where it was. It could be in quadrant 1, quadrant 3, quadrant 2. It doesn't matter where it's at. Any xy coordinate in the xy plane actually establishes a signed width and a signed height for a right triangle. So if I take from the xy coordinate and drop a perpendicular, the signed height of the right triangle that I form, that's opposite my reference angle, is going to be height y, and the width of it, the signed width, is going to be x. And it could be down here in quadrant 3. I'd get the same thing. Drop a perpendicular. Here's my reference angle. This width is going to be just the x coordinate. It's a signed width. And the height is just going to be the y coordinate. It's a signed height. And if I wanted the width in an unsigned fashion, I would just take the absolute value of these numbers, and then I would have an unsigned width and an unsigned height. So the idea, because x is a horizontal measurement, it gives me width, and because y is a vertical measurement, it gives me a height. And if we have a width and a height on a right triangle, we can use the Pythagorean Theorem to calculate the hypotenuse of the right triangle. So this hypotenuse here, which also establishes a circle in the xy plane. So sometimes in the xy plane we'll represent this with r for radius instead of h for hypotenuse. The idea is the Pythagorean Theorem tells us that the square of the hypotenuse, or the square of this radius, which is part of a right triangle, is just going to be equal to the sum of the squares of the legs. So even if we use absolute values, because we don't want signed width and signed heights, we want to get rid of the negative signs, even if we did that, we would still wind up with, hey, these right triangles that we established by dropping perpendiculars have widths absolute value of x and heights absolute value of y. And if we square a number, we really don't need the absolute value sign, because we're going to generate positive results anyways. So we get r squared equals x squared plus y squared, where r is just the hypotenuse of this right triangle, or the radius of this circle. And so we want to know what r is. We just take the square root of both sides, and we don't need to take plus or minus the square root, because when we're talking a hypotenuse or a radius, we're talking a positive real number usually. So we can calculate the length of this line segment from the origin to any point xy we want, from the origin to any point xy we want in the xy plane, using the Pythagorean Theorem and then taking the square root of both sides. So we did that so that we could use that radius here in a definition. So here's the definition for trigonometric functions in the xy plane. It says, hey, let xy be any point on a circle you want, or not on a circle, any non-origin point in the xy plane. So once you establish a point xy relative to the origin, you can make a circle that contains it. So maybe I put my point xy up here in quadrant 2. So xy is any point in the plane that isn't the origin, and then theta is the angle in standard form that you would construct using that point. So here's theta, and then theta r would be the reference angle for that point. So if I drop a little perpendicular, theta r is the reference angle on this right triangle. And r is just the length of this line segment, which we calculate using the square root of x squared plus y squared. It comes from the Pythagorean Theorem. So as long as theta isn't a quadrantal angle, we can come up with these nice definitions. So the sine of theta in the xy plane, whether we have a quadrantal angle or not, is going to be the y-coordinate divided by the hypotenuse or the radius. And what we want to notice is that the y-coordinate, if I establish an xy point, the y-coordinate actually gives me the signed height opposite the reference angle. And the x-coordinate gives me the signed width opposite a right triangle formed by the reference angle. So in terms of the definition that we already had established, we had said the sine of theta is the side opposite theta over r. Well, now the sine of theta is going to be the side opposite the reference angle for theta. So in this case, y is opposite the reference angle, and then it's over the hypotenuse or r. So it's really a similar definition to what we've already established. It kind of flows directly from it. So in the xy plane, sine of theta is going to be y over r, but y is just going to be the side opposite the reference angle, and that's why we wasted some time talking about reference angles. The cosine of theta is just going to be the x-coordinate over r, or the hypotenuse. But notice that the x-coordinate is the side adjacent the reference angle. So it's side adjacent over r. The same definition that we had before, but now we're constructing our right triangles using the reference angle. And then the tangent of theta, we're going to define it to be the ratio of y to x. So we take the y-coordinate, divide it by the x-coordinate, but we want to notice that this is consistent with how we've already defined it using right triangles, because the y-coordinate is the side opposite the reference angle, and the x-coordinate is the side adjacent the reference angle. So we still have an opposite over adjacent definition for the tangent function. And then the reciprocal functions are exactly the same that they were before. The reciprocal of sine is cosecant, so you just take the ratio you used to define sine and write its reciprocal. The secant is still defined to be the reciprocal of the cosine function, so the ratio you use to define the cosine function, you write its reciprocal for the secant. And similarly, the cotangent is defined to be the reciprocal of the tangent, so the ratio you use to define the tangent function, you use its reciprocal to define the cotangent function. So again, these are really consistent with how we defined trigonometric functions using a right triangle. The slight difference now is we're saying that we're going to take the ratio of the side opposite the reference angle, or the side adjacent the reference angle. We do everything with respect to the reference angle, and now because we're in the xy plane, the sides that are opposite and adjacent may have negative signs on them depending on the quadrant that you're in. X is negative if you're in quadrants 2 and 3, and the y-coordinates will be negative if you are in quadrants 3 and 4. So we'll have signed ratios now instead of positive ratios. That's really the big difference. So let's go and use our trigonometric function definitions to find the exact values of all 6 trigonometric functions. So what we're being given is a point in the xy plane, and I'm going to ignore the tick marks and just kind of roughly sketch these points in. I'm going to pretend like I see no tick marks and they haven't been assigned any values. So 5, negative 6 would be like over 5, down 6. This would be 5, negative 6, ignoring the tick marks on purpose. That establishes a point in the xy plane. And there is an angle theta that goes with it. And then there is a reference angle theta r that goes with that point. And I can drop my perpendicular and get my right triangle relative to the reference angle. And then we can walk through and get the 6 trigonometric functions. What we want to recognize is that this horizontal width is 5, and this vertical height comes from the y-coordinate. It's negative 6. And then we can use the Pythagorean Theorem to come up with this length right here. So we called this length r. And so we know from the Pythagorean Theorem that r is going to equal the square root of the sum of the squares of the legs of the right triangle. And one leg is a 5, And the other leg of our right triangle is a -6 because we're allowing signed distances. And this is just going to give us 25 plus 36, which is just going to be square root of 61. So our hypotenuse or radius measurement is the square root of 61. And then we just walk through and use the definitions. The cosine of theta is the x-coordinate over the radius, or the side adjacent the reference angle, divided by the hypotenuse. We could rationalize this if we wanted to. I don't think it's necessary, but some homework platforms will require that you rationalize this denominator. We can find the sine of theta, which is defined to be y over r, the y-coordinate over the radius, or using our right triangle definition, it's the side opposite the reference angle over the radius or hypotenuse, so a -6 over the square root of 61. And finally, the tangent function, the tangent of theta, is defined to be the y-coordinate over the x-coordinate, y over x, or the side opposite the reference angle, which is the y-coordinate, -6, divided by the side that is next to or adjacent the reference angle, which happens to be 5, or the x-coordinate. And then the reciprocal functions are easy. The reciprocal of cosine is secant. So the secant of theta is just the reciprocal of the cosine function. So it's the square root of 61 over 5. The reciprocal of the sine function is the cosecant function. So the reciprocal is going to be negative square root of 61 over 6. And the reciprocal of the tangent function is the cotangent function. So instead of -6/5, we get -5/6. So sometimes we're asked to find the trigonometric values of the trig functions, and we're not given the point. We're just given some information about it. So here we're told what the secant is. We're told that the secant of theta is 9 over 8. And so we need to remember 9 over 8. We need to remember that the secant is the reciprocal of the cosine function, and the cosine function is defined to be the x-coordinate divided by the hypotenuse or the radius. So the secant function has to be the radius divided by x. So what we can see from this is that because radius is always a positive number, the radius, the hypotenuse length, is always positive. We see that if the radius is 9, x must also be a positive number, because if x were negative, we would get a negative value here. We would get -9/8. So x is 8, r is 9. Just reading straight from the definition, the radius is 9. It's r over x for our ratio. X is 8. X has to be positive. If x were negative, then this ratio would be negative. And then they tell us a little something more. They say, hey, the tangent of theta has to be a negative number. And then we need to think about, how was the tangent defined? Well, the tangent was defined as opposite over adjacent with respect to the reference angle, or the y-coordinate over the x-coordinate. So the only way for the tangent to be less than 0 or negative is for one of these two numbers to be negative and the other to be positive. But we already know that x is equal to 8 and it's positive. That means y must be a negative number. So y needs to be negative. And the only places where y is negative is if we're below the x-axis. So we either need to be in quadrant 3, we're either over here in quadrant 3, or we're over here in quadrant 4. Those are the only two places we get a y value that's negative, which would make the tangent function be less than 0. But if we're in quadrant 3, then x would also be negative. X is negative and y is negative in quadrant 3, but we know x is positive. X is only positive in quadrant 1 and 4. And so the only place we get an overlap is in quadrant 4. That tells us that our point, our xy coordinate, is in quadrant 4. So we have some point living over, we have some point xy living over here in quadrant 4 that has an angle theta associated with it and a reference angle associated with it. We drop the perpendicular. Now I have a right triangle. I already know the width of that right triangle is 8. It's the x-coordinate. This is 8. I know the x-coordinate. I don't know the y-coordinate, but I do know the radius is 9. And I got that from the definition of the secant function. And then the last thing I need to figure out is what is y, but that's just a Pythagorean theorem issue, right? The Pythagorean theorem says that the square of the hypotenuse equals the sum of the squares of the side of the legs of the right triangle. But the legs are the x and the y coordinates. And then we just need to solve this. So we get 9 squared is 81. Subtract 8 squared from both sides. And then we get 81 minus 64, which is going to be 17. That's going to be a 17 equals y squared. And then usually when you do the square root of both sides, you go plus or minus. That's to get the y by itself. But here we know that we don't want the positive square root. We want the negative square root because we're in quadrant 4 and the value of y is negative in quadrant 4. So here's the y coordinate, which gives me my signed height, negative square root of 17 on my right triangle. Now I have everything I need to do to get the exact values of all of the trig functions. I might as well start with the secant because it's given. So I've got the secant of theta, and its reciprocal is the cosine of theta. So if the secant of theta is 9 over 8, then the cosine will just be the reciprocal of that. And then the sine of theta is defined to be the side opposite the reference angle, or the y-coordinate, divided by the hypotenuse or the radius, which is 9. And its reciprocal function is the cosecant function. So the cosecant function we get for free once we have the sine function. It's just the reciprocal. And finally we can get the tangent function. The tangent function is defined to be the y-coordinate over the x-coordinate, or the side opposite the reference angle divided by the side adjacent the reference angle. So it's going to be negative square root of 17 over 8. And we get the cotangent for free because the cotangent is just the reciprocal of this, or negative 8 over the square root of 17. Again, if we were inputting answers into a computer algebra system, we would need to do something like rationalizing this denominator. That's usually a requirement in a computer algebra system. I don't think it's particularly necessary, but if your homework system expects that, then you need to do it. So here's another example. I say let theta be an angle in quadrant 3. So now we're being told where we are. The previous example we had to figure out which quadrant we were in. That was a mystery. Now it's not a mystery. We're told that we're in quadrant 3. So it's quadrant 1, 2, 3. We're in Q3. Which means we know the x-coordinate is negative and the y-coordinate is negative. Both x and y are negative values in quadrant 3. And we're told that the cosine of theta is negative 12 over 13. And we know that the cosine is defined to be the x-coordinate, or the side opposite the reference angle, divided by the radius or the hypotenuse of the right triangle. So we have some angle here in quadrant 3. So we're sweeping through some angle theta into quadrant 3. There's a reference angle associated with theta. We're going to have an x and y coordinate that we're working within quadrant 3. And just looking at this, I know x is negative. So from here I can see that x will be the negative 12 in the numerator. The radius is always positive, so we know this has length 13. We know the x-coordinate is a 12. We don't know the y-coordinate. The y-coordinate is going to give us the signed height of the right triangle associated with the reference angle. I know the width of this right triangle is the x-coordinate. The x numbers gives us the width, so the signed width is negative 12. So to find out what y is, we just use the Pythagorean theorem. Here's my hypotenuse. The hypotenuse squared equals the sum of the squares of the legs of the triangle. So my x-coordinate is one leg, my y-coordinate is the other. So I have 169 when I square 13. When I square negative 12, I get 144, and I'm going to subtract that 144 from both sides. 169 minus 144 is a 25. I'm going to take the square root of both sides to get y by itself. Usually you go plus or minus, but again, in quadrant 3, y is negative, so we don't get the positive square root. So we find that the y-coordinate is negative 5. So I step over here. Here's my negative 5, which means the side opposite the reference angle is going to have a signed height of negative 5 units. This is a right triangle right here. And now we can find the values of our 6 trig functions. We already know the cosine because it's given, so you might as well grab it first because its reciprocal is the secant function, which means you get it for free by simply writing the reciprocal of this side ratio. Now the sine of theta is the side opposite the reference angle, which is the y-coordinate, divided by the radius, which is 13. And the reciprocal of the sine is the cosecant, so we get negative 13/5 by taking the reciprocal here. And then the tangent is defined to be the y-coordinate divided by the x-coordinate, or the side opposite the reference angle, which is negative 5, divided by the side adjacent the reference angle, which is negative 12, which just simplifies to 5/12. And then the cotangent function we get for free because it's just the reciprocal of the tangent function. So we've got one last example to do. So here we're given that we're in quadrant 4, so we're told that we're over here in quadrant 4, quadrant 1, 2, 3, 4. Here I'm in quadrant 4. In quadrant 4, what do I know? I know the x-coordinates are positive. I know the y-coordinates are negative because we're below the x-axis. And then we're told that the tangent of theta is equal to negative 4/3. And we know that the definition of the tangent function in the xy plane is that it's the ratio of y to x, or the side opposite the reference angle divided by the side adjacent the reference angle. So in this case, the question is, does the negative sign go with the 4 or the negative sign go with the 3? But because we're in quadrant 4, the x has to be positive 3, and the y value needs to be the one that gets the negative sign on it. So we've got an over 3 down 4 kind of a thing going on in quadrant 3. So we've got this 3 comma negative 4. We don't know the radius. If I drop a perpendicular, it's going to be associated with a reference angle. Theta is going to be this angle wrapping around to here. We don't need to use it, but that's the angle that it is, or an angle that it could be, because it could be any coterminal angle as well. And then we just need to calculate the length of this hypotenuse. So r squared, or the hypotenuse squared, equals the sum of the squares of the legs. One leg is 3. One signed leg is negative 4. So applying the Pythagorean Theorem, and we get 9 plus 16 is 25. And take the square root of both sides. This time we don't do plus or minus because the radius or hypotenuse is always a positive value in this context. So we get a 5 on there, and then once we have that, we can go through and do the trig functions. Again, start with the one that you know, which is the tangent. The tangent of theta is negative 4/3. So the reciprocal must be negative 3/4. Now get the cosine function, which is the side adjacent the reference angle, or the x-coordinate, over the radius, which is 5. Now you get his reciprocal, the secant function, for free. He's 5/3. And finally do the sine function, which is equal to the side opposite the reference angle, which is the y-coordinate, over the radius, and his reciprocal is the cosecant, so we get that for free.